Welcome to the class. Today we will have the third lecture on planning. In the last two classes, we have looked at state space, looked at planning in artificial intelligence, and we have looked at representations of planning problems. We have looked at the strips representation, the strips algorithm for solving planning problems, and we have also looked at regression planning and progression planning, which involve searching in the state space to find the plans. Today, in the third lecture, we will explore further the details of partial order planning. As I have mentioned in the previous class, in partial order planning, we will be searching in the space of partial plans. And our objective is, given a problem situation, we want to get a plan which makes least commitment about the ordering of the different actions. So, we will represent the plan as actions and the ordering between the actions in order to get the final plan of the problem. In any intermediate stage, we will maintain consistent partial plans which may not be complete, and we will presently see the details of what I mean by this. So, in partial order planning, the nodes would be partial plans, and to get from one partial plan to another partial plan, the step is called plan refinement. By taking a partial plan, by doing plan refinement, we get to another partial plan. And the solution to the planning problem is a partial plan. So, the path to the solution is not important, because all the relevant information is captured in the partial plan, which is a node in this state space search, in this search problem. That is, we obey the principles of least commitment. We do not commit to any ordering of the actions which is not required. So, before we continue on this, if you remember the simple socks and shoes, putting on socks and putting on shoes problem that we mentioned in the last class. So, if you can recall that, you remember our objective is to put on the left sock, left shoe, right sock and right shoe. So, these are the four conditions that must be satisfied at the goal, and one cannot put on the right shoe before the right sock is put on, or the left shoe before the left sock is put on. And a solution to such a problem would be, after the start, the agent can put on either the left sock or the right sock. Only after the left sock the agent can put on left shoe. Only after right sock the agent can put on right shoe. When both left shoe and right shoe are on, the plan is done or finished. So, this represents a partial plan for the socks and shoes problem. An actual plan will of course not be such a partial order structure, it will be a linear structure. From this partial order structure, we can get several linearizations. The agent can put on left sock, left shoe, right shoe, or left sock, left shoe, right shoe, or right sock, left shoe, right shoe, or right sock, right shoe, and so on. So, how many, can you tell me how many linearizations will be possible given this partial plan? So, I leave you to work that out, and let us get to certain terminologies that we will be using today. A step in the partial plan, we have a step in the partial plan, and a step in the partial plan would be a particular action which is taken. So, a step is bound to a specific action. Then in a partial plan, we will have orderings of the form S1 before S2, which means S1 must precede S2. Okay. If S1 is an action, S2 is another action, action S1 must come before the action S2. It may come immediately before the action S2 or sometimes before the action S2. Thirdly, let us see what we mean by open conditions. Open conditions are preconditions of the states of the steps which have not yet been satisfied. Okay. Suppose we have a step, and in order to execute the step, we need certain preconditions to hold. As you know, in the strips representation, for every action we have preconditions. Say, let us say P1 and P2 are preconditions of action A, and also, as you know, for every action we also have the add list and the delete list. Suppose Q1 and Q2 are added and Q3 is deleted. So, P1 and P2 are the preconditions of the action A. Open conditions are those preconditions of the step A that have not yet been satisfied. Then we need to look at what we mean, this is very important, we need to know what we mean by causal link. Now, we will say that AP to AC on Q is a causal link on Q if AC, the step AC has a precondition of Q and this precondition is met by the step AP. If the step AP supplies the precondition Q, which is a precondition of AC, then AP to AC is a causal link on the condition Q. So, this is a commitment that the condition Q needed by AC will be made true by AP. That is, AP must cause AQ, AC. So, AP must have Q as an effect and AC has Q as a precondition. Now, we say that AP achieves Q for AC. So, let me write that. So, AP achieves Q for AC. Now, if in our partial plan AP achieves Q for AC, what it means is that no action can come between AP and AC which deletes Q. So, while developing the partial plan, if we want AP to achieve Q for AC, we must make sure that no action would come between AP and AC which deletes Q. Okay. Now, more terminology, unsafe link. Suppose there is a causal link S1 and S2 on the condition P, and then we have another action S3. Now, if I put S3 between S1 and S2 and S3 can undo P, then S3 will not be able to come between S1 and S2. So, if my plan permits or if my partial plan permits S3 to come between S1 and S2 and S3 deletes P, then this is an unsafe link. This causal link S1 to S2 on P along with S3 together, this is an unsafe link. So, such unsafe links have to be taken care of before we get the final plan. Okay. Now, before we discuss the planning, the partial order planning algorithm, we will first in order to develop the algorithm, we will start with the initial state. The initial state is a initial partial plan, and we will start with this. The empty plan is given by this. Empty plan, in the empty plan we start with an initial state I, a goal state G, and we assume that I precedes G. There is an ordering between I and G. I precedes G, and at G the preconditions that have to be satisfied are, suppose G is G1 and G2. So, G1 and G2 are the open preconditions that must be satisfied at G. Initial plan, there are no causal links and there are no unsafe links, but this plan is not complete because G1 and G2 are the open preconditions. Now, let us look at how we will represent partial plans. A partial plan is represented by a 5 tuple. I think in the next slide we will have a bigger picture. Okay. So, a partial plan is represented by a 5 tuple A, O, L, O, C and U, L. What is A? A is a set of actions in the plan. A is the set of steps in the plan. So, S0, S1, S2 up to Sinf, let they be the steps in the plan. So, a plan consists of the set of steps, and as I mentioned, a partial plan is not necessarily a total order plan. That is, it is not just a sequence of steps. We can order the steps according to a partial order. So, we have a set of steps and we also specify the set of action ordering. So, there is a partial ordering on the actions. Si precedes Sj denotes that Si, the step Si must occur before the state Sj in a realization of the plan. So, A is the set of steps, O is the set of action orderings and L is the set of causal links. And as we saw, a causal link Si to Sj on condition P means Si achieves condition P for Sj. So, Si has P as an effect and P is a condition, precondition that is required by Sj. Okay. So, A, O and L specify the partial plan. Now, in a partial plan, we have a set of open conditions which we denote by OC. So, OC is at the sub goals, represent the sub goals that remain to be satisfied. They could be the sub goals of the final goal or they could be the sub goals of an intermediate state. The sub goals of a or the preconditions of an intermediate state which have not yet been satisfied. So, open conditions means those conditions that are not satisfied and therefore, the plan is not yet complete. And then we have a set of unsafe links. So, if we have the causal link Si achieves P for Sj and there is a step Sk which deletes P, then Sk cannot come between Si and Sj. So, if in a partial plan Sk can come between Si and Sj, we have an unsafe link. So, what does a plan consist of? A plan is a 5 tuple So, we have three things: A is a set of steps in the plan, O is a set of partial order relations between these steps, L is the set of causal links, and in a plan there are certain, if the plan is not complete, what we will have in the plan is a set of open conditions, which are the set of sub goals that have not yet been satisfied, and we have some unsafe links which consists of causal links and a step which can come between the two steps in the causal link and delete the condition which is required. So, now when we have a partial plan, that plan is flawed if there are some open conditions or there are some unsafe links, and the solution plan would be a partial plan which has no remaining flaw, that is, it achieves all the conditions and there is no unsafe link. So, in the final solution plan that we would like, there must be no remaining flaw. It is every open condition must be satisfied by some action, and then no unsafe links should exist. Now, this is a representation of the partial plan. We introduce two distinguished states, S0 for the initial state and S-inf for the goal state. Now, we will consider that the initial state description is an effect of the initial step. So, if in the problem the initial state is Q1, Q2 and the goal desired to be achieved is G1, G2, then we will have an initial state S0 whose effect will be Q1, Q2. And so, Q2 is another effect of S0, and G or S-inf is the goal state, and for this goal state it has a set of preconditions. The preconditions are the propositions which are true at the goal state. So, the preconditions here are G1 and G2. So, in the initial plan that one can draw, G1 and G2 are the open conditions. So, this is S0 and this is S infinity, and G1 and G2 are the open conditions of G. Now, this is a partial plan where this open condition G1 is achieved by S3. So, S3 achieves G1 for S-inf, and let us say S1 achieves P for S3, I achieves Q1 for S1. Also, suppose S2 achieves G2 for S-inf, and now suppose S2 has an effect of not P, that is S2 deletes P, and S1 achieves P for S3. Can you tell me if there are any unsafe, any flaws in the plan? There are two types of flaws in this plan. Firstly, S2 is a step which has two preconditions OC1 and OC2 which are not yet satisfied. So, OC1 and OC2 are the open preconditions of the step S2. So, this is flaw number 1. Secondly, the flaw number 2 is, you see, S1 precedes S3, S3 precedes G and S2 precedes G, but we have not said anything in this partial plan about the relative ordering of S1, S2 and S3. Now, if I put S2 between S1 and S3, so if I, in a linearization, if we have S0 to S1, S1 to S2 and S2 to S3 and then S3 to done, can you tell me what is the problem? The problem is S1 will have P as an effect, but that P would be deleted by S2. So, S3 will not get P as a precondition. Okay. So, because S3 requires P as a precondition, which is supplied as an effect of S1, we cannot put S2 between S1 and S3. So, this is not correct. Okay. So, what can we do? So, S2 can occur either after S3 or it can occur before S1. Okay. S2 which deletes P cannot come in between S1 and S3. It can come before S1 or after S3. Now, let us look at a very basic version of the partial order planning algorithm. Let P be an initial plan. Now, given an initial plan, we first find out if the plan has any flaw. So, P is a plan, we find out if P has a flaw. So, we choose a flaw F. The flaw could be an open precondition or it could be an unsafe link. Then once we have selected a flaw, so a partial plan may have several flaws. We choose one of them. Okay. Actually, eventually we have to remove all the flaws in the planning algorithm, and the order in which we choose the flaws may have a bearing on how fast we solve the problem. But irrespective of which flaw we choose first, we can choose the flaws in any order and we will get the same solution. So, we have to choose a flaw, and depending on the nature of the flaw, we have to take certain steps. So, as we mentioned, flaw is of two types. An open condition is a flaw, or an unsafe link is also a flaw. If we get a flaw, select a flaw which is an open condition, then what should we do? So, we should choose an action S that achieves this open condition. So, if F is an open condition, so suppose there is a state S prime and this state has F as its precondition. Okay. Now, in order to correct this flaw, we must choose a state, another state S 1 which has F as an effect. Okay. If we do this, then this open precondition is taken care of, even though other flaws might be introduced. Namely, the preconditions of S prime, if they are not satisfied, there will be new flaws that are introduced. Secondly, a flaw could be an unsafe link. If the flaw is an unsafe link, that is, if we find that S2 deletes F, then S2 cannot come between S1 and S prime. So, S2 can either be promoted to come before S1 or it can be demoted to come after S prime. So, this is a protected interval between S1 and S prime, where S2 that undoes the effect of F cannot come. So, S2 can be promoted or S2 can be demoted. Now, after we have done that, we must update the partial plan. So, if we promote S2, then we must add a causal link between S2 and S prime S1, from S2 to S1. If I put S2 after S dash, then we must add a precedence link from S dash to S2. And while doing this, if we find that there is no operator by which we can resolve the conflict, then we return null. This planning algorithm does not succeed. But if it does succeed and if we come to a point where there is no flaw left, then we will return the current plan. Otherwise, if there are more flaws left, we will go to step 2 and select the next flaw. Okay. So, is this algorithm clear to you? We start with an initial partial order plan which consists of the initial state I, the goal state G. The goal state has the desired propositions given as a goal as its open condition. The initial state has the initial state description as its effect. Now, our algorithm will choose a flaw. A flaw is either an open condition or it is an unsafe link. If the flaw that we have chosen is an open condition, we must choose an action S that achieves F. If F is an unsafe link, then we will choose to promote or demote our current plan, the current step in the plan. And once we have done this, we update the current plan. We return null if no resolution exists, and if there is no flaw left, we return P, else we go back to state 2 and continue. So, this is the initial plan, S0 is the initial state, Sinf is the final state, G1 and G2 are the open conditions of Sinf. This is an intermediate partial plan. Here we have Sinf. Sinf has the preconditions G1 and G2. S2 achieves G2, S2 deletes P. S3 achieves G1 for Sinf. S1 achieves P for S3. S1 has Q1 as its prerequisite. S2 has OC1 and OC2 as its prerequisites. So, if I take this open condition, I must add a step which has OC1 as its effect. If I look at this causal link from S1 to S3 on Q and this node S2, if we put S2 between S1 and S3, then we can correct the flaw. So, this process of flaw selection and flaw resolution is known as plan refinement. So, this is an example of a partial plan. Apart from the initial state S0 and the final state, this is the initial state and the final state Sinf, we have 3 other steps S1, S2 and S3. S3 achieves G1, S2 achieves G2, S2 deletes P, S1 achieves P which is required for S3. S1 has a precondition Q1, S2 has 2 preconditions OC1 and OC2. So, can you tell me from this example what are the flaws in this partial plan? Now, there are several flaws in this partial plan. Firstly, there are 3 open preconditions. S1 has the condition Q1, S2 has the condition OC1 and OC2. Secondly, there are some unsafe links. S2 cannot come between S1 and S3 because S2 deletes P which is required by S3. So, for flaw selection we have several choices. The choices are the open conditions in the plan and the unsafe link. The flaw resolution deals with how we select partial plans. Here we can select a particular action and treat this as a backtrack point, or even for finding the unsafe links we can use backtrack search. So, this is a repetition of what I said earlier. A partial plan is a tuple, is described by the tuple AOL. A is the set of actions in the plan, O is a set of temporal orderings, A of the form A precedes B, and L is the causal links linking actions via a literal. This is an example of a causal link. AP achieves Q for AC. Action AC has precondition Q that is established by the plan by AP. Another example, when one moves A from B to the table, the effect is to clear B, and clear B is required to move C from D to B. Now, when we have an unsafe link, as we noted, a step, there is a step which can come between a protected link. So, we say that a step AT threatens a link AP achieves Q for AC if number 1, AT has not Q as an effect. Secondly, if AT could come between AP and AC, that is, if according to the partial plan we can put AT between AP and AC. In both these cases, there is a problem with the partial plan, it is not fully correct. So, let us look at the initial plan. For uniformity, we represent the initial state and the goal state with two special actions. A0 is a special action or S0 which has no precondition, which has the initial state as effects, and they must be of the first step in the plan. A OD has no effects, goals are preconditions and must be the last step in the plan process. Now, let us look at the partial order planning algorithm in slightly greater detail by seeing how we proceed. So, the partial order planning problem POP stands for POP, takes three arguments AOL. A is a set of steps, O is a set of temporal orderings between steps, and L are causal links linking actions with the liberal. So, the POP algorithm takes AOL as argument. In addition, it takes two other arguments, agenda and the actions. Agenda are the set of flaws and actions are the set of actions that the agent can take. If agenda is empty, then return AOL. So, we have called POP or partial order planning on AOL as also agenda and actions. If agenda is null, then we are done, we return AOL. If agenda is null, then return minus AOL. Add equal to chooses actions such that O is using effects. So, if we have initially the agenda is empty, if the agenda is empty, we return AOL, otherwise we pick up a flaw from the agenda. Let the flaw be QA need. So, let the flaw be QA need. Now, in order to satisfy this flaw, we must choose an action such that Q, this action requires Q. So, we must pick an action which adds Q. So, we have to have an action which adds Q. So, A add is such an action. If no such A exists, then we return failure. Otherwise, we put L prime equal to L union A add is the current step, Q is the A add is the current precondition, current step, the new step that we have obtained, Q is the what A add achieves and A need is what Q needs. So, in other words, let me just draw this. You have an action A need. This step A need has a precondition of Q which has not yet been achieved. So, we find an step A add which has Q as its effect. Now, in this case we can say that A add achieves Q for A need. Now, A add is a new step. Because it is a new step, then we must add the preconditions of A add which are not satisfied to the agenda. Now, how is the planned data structure changed? First of all, in the planned data structure we add a causal link from A add to A need on Q. Secondly, we update the partial ordering relations by adding this new relation A add must come before A need. Then agenda, the new agenda is one entry that we have removed from the agenda is Q A need, because Q, which is open precondition for Q, has been achieved in this state. So, we remove it from the agenda. If A add is new, then A equal to A union A add. That is, if you have got a new step, then I will add it to my action list. And then for all preconditions of A add, we must add P A add to the agenda. Then for every action A that threatens any causal link, so we have taken care of open preconditions. Next we have to take care of unsafe links. Now, for every action AT, we check if it threatens any causal link. If it does threaten any causal link, we must put the action AT either before AP or after AC. So, I have already drawn that diagram. You have AP which achieves AC and it achieves it on the state variable Q. Now, our objective, when we want to bring in a new step, I must either bring it before AT or I must bring it after AC. Okay. Finally, if the search succeeds at all points and we have a agenda which is empty, then we get the answer. So, this is the same algorithm written in a small fashion. Initially, we are given a partial order planning problem comprising of AOL, agenda and actions. If agenda is empty initially, then we return the current plan AOL. Otherwise, we pick Q A need from agenda. This is an empty condition. Q is an empty precondition of A need. So, we select our current goal. Then we choose an action which achieves this effect Q. If there are several such actions, this is a choice point. If there is no such action, of course, the search will fail. And then we say L dash equal to L union A add Q A need. So, L is the set of causal links. We add the causal link from A add to A need on Q to L. So, this is A add, this is A need and this is Q. Now, O dash will be, O dash is the set of constraints, precedence constraints. I add A add comes before A need. Agenda, from agenda I remove Q A need. If a new step is added, then I union it with the step list, and for each preconditions of the new state we add it to agenda. For every action AT that threatens any causal link, we choose to add that AT is before AP or AC is before AT, etc. If neither choice is consistent, fail. Now, this is the same algorithm written in big. So, initially I pick an goal, then I choose one of the actions, then corresponding to the action I update the goals, that is I remove q init from the agenda, then I add a new step, I find the preconditions of the new step, and for every action AT that threatens any causal link. So, suppose we find that there is a causal link from AP to AC on Q, and if we find that there is an action AT which threatens AP and AC, we say AT must occur before AP or AT must occur after AC. If AT cannot occur before AP or after AC, if they are not consistent, then we fail. And then we recursively call POP on the action list, on the causal link list, and on the goal list. So, as you can see, the partial order planning problem is sound and complete. The POP plan is a solution if all the preconditions are supported by causal link, that is, there are no open conditions, there are no threats to any causal link, and we have a consistent temporal ordering, and by construction the POP algorithm reaches a solution plan. Now, we will illustrate this POP algorithm with a very simple example, the Bloxwald example of the Sussman anomaly, which we have discussed earlier. In this problem, the initial state consists of 3 blocks C, A and B placed as follows: A and B are on the table, C is on top of A. The goal is to get the 3 blocks stacked like this: A on top of B, B on top of C. Before we do our POP algorithm on this problem, let us look at the representation of the initial state and the goal. The goal is represented by A is on B and B is on C. Note that we mentioned that we can have a subset, we can represent a goal by a subset of the conditions that hold. So, the initial state is specified by the exact behavior of all the variables. In this case, on table A and on C A and clear C, on table B and clear B. So, this is the description of the initial state, and on AB on BC is the description of the goal state. Now, we will work out this example of the Sussman's anomaly now. A0 is the initial state or I, and A inf is the goal state or G. It has 2 open preconditions on AB and on BC. So, what are the flaws in this plan? I has these as the effects. So, flaws are there are 2 open preconditions. Now, what should we do? We will try to take one of these open preconditions and try to satisfy it. Now, in the first step, if we have an action or step A1 which involves moving B from table to C. If I move B from table to C, what do we achieve? We achieve the precondition on BC. So, on BC is an effect of the action move B from table to C, and on BC is required by the goal. So, we have a causal link on BC. Then, before we proceed, let us see what are the open conditions, what are the flaws in this partial plan. There are several open preconditions. On AB is open, clear B is achieved in the initial state, but here it is open. Clear C is achieved in the initial state, but here it is open. On table B is achieved by the initial state. Now, what we will do is we will take up one of these open conditions. Let us take up clear B, and we see that clear B is satisfied in the initial state. So, we say that A0 achieves clear B for A1. Next, we look at the open condition on AB on this subgoal. Now, to achieve on AB, we introduce a second step A2, which says move A from table to B. Now, move A from table to B has preconditions clear A, clear B on table A, and effects not on table A, not clear B on AB. Now, this on AB achieves this on AB. Now, what are the open conditions? Clear A, clear B on table A. Now, we notice that A0 achieves clear B for A1, but A2 removes clear B. So, clear B is required by A1 and this clear B is achieved by A0. Now, this step A2 deletes clear B. So, A2 cannot come between A0 and A1. So, A2 must come before A0 or after A1. A0 is the first state, is the special first state. A2 cannot come before A0. So, A2 must come after A1. So, recognize this fact, we add an ordering constraint from A1 to A2. So, A0 is followed by A1, A1 is followed by A2, A1 is followed by A-inf and A2 is also followed by A-inf. So, this is what this particular partial plan represents. Now, we pick up the open precondition clear A, which is required by A2. Now, we introduce an action A3 that achieves clear A. What is the action A3? Move C from A to table. So, if you move C from A to table, then A becomes clear. The other effects are not on CA, on table C and clear A, and the preconditions are on CA and clear C. So, this is another step A3. So, right now we have introduced 3 different steps in our plan, A1, A2 and A3. Now, these are the pink arrows are the causal links between the states and the white arrows are the the ordering links between the steps. Now, finally, we see that on CA is achieved in the initial state, clear C is achieved in the initial state, that is for action A3. For action A1, clear B, clear C on table B, all are achieved in the initial state. For action A2, clear A is achieved by A3, clear B by initial state, on table A by initial state and so on. And we finally find that the ordering relations are A3, then A1, then A2. So, why A3 then A1? Because actually A3 and A1 can come in any order. And no, yes, you see A1 deletes clear C, A3 requires clear C. So, we cannot put A1 between A0 and A3. So, after A0, so to protect this unsafe link, we must add a ordering constraint from A0 to A3. So, finally, we get a plan A0 to A3 to A1 to A2 to A-inf, which is a plan which meets this goal. So, the steps are move C from A to table, move. So, if you recollect the planning problem, the goal was A on top of B, B on top of C, and in the initial state I think we had C on A and B on the table. Now, what are the steps? First move C from A to table, then move B from table to C, move A from table to B, and then we are done. Now, in summary, you see, if we compare partial order planning versus state space planning, you see the complexity of a search problem is O b to the power n in the worst case, where B is the branching factor, and we have non-deterministic choices. Now, in progression planning and regression planning, n is the number of the size of the plan, the depth of the plan is the number of actions in the plan. In POP, the depth is the number of steps that we have to take to satisfy the flaws. What are the flaws? The flaws are the preconditions, open preconditions and the unsafe links. So, the n is related to the number of preconditions of the steps and the number of link protection that we require, and generally an action has several preconditions. Now, if we look at the branching factor, POP usually has a smaller value of the branching factor, but the main advantage of POP is that we have no backtrack due to goal ordering. We have a backtrack when we have to satisfy an open condition, there could be more than one action which satisfies the precondition. So, there is a choice point. So, there could be some backtracking on deciding which action to use to achieve this precondition. But if we have two sub goals G1 and G2, let us say on AB and on BC, we do not have to backtrack on which one first, whether we should do on AB or whether we should do on BC. We can do both separately, and then while deciding whether we should take this action first or this action first, we look at what conflicts they generate, we look at the unsafe links. So, there is no backtrack due to goal ordering. In partial order planning, as we have noted, we have this list commitment, that is we do not do any premature step ordering. So, we usually the search involved is less if we do partial order planning. Okay. So, with this we end today's lecture. In the next class, we will have the last lecture on planning, where we might introduce some techniques to speed up planning even further. Thank you.